Hello, welcome to our YouTube channel Tech LT World. Today we'll be discussing about a very important topic in LT, that is LT throughput calculation. So let us begin. So we start calculating the throughput in LT, there are certain factors which affects throughput in LT and we need to understand that. So here are the, if you can see the slide, there are certain points or factors we can say that affects the throughput in LT. First is the system bandwidth. Okay, as we know in LT there are it consists of flexible bandwidths. It supports certain bandwidths which are flexible in nature, right? It supports 1.3 megahertz. It supports the 5 megahertz bandwidth, 15 megahertz, and also 20 megahertz, right? So it can support certain this range of bandwidths in the spectrum, right? So and each bandwidth will basically consisting of different size of resource block, and hence it affects the throughput in LT. We'll be discussing about each factor in detail in upcoming slides. So besides system bandwidth, there are other factors also like multiplexing technique. So if you all have seen our previous video, so in LT there are two kinds of multiplexing technique, right? So the first one is the TDD, it is time division multiplexing. Another is the FDD, it is frequency division multiplexing. So uh, each of these multiplexing technique can affect the throughput in LT. The third factor which affects the throughput in LT is the modulation and coding scheme. So as we know, there are certain modulation scheme which LT can support, like QPSK, 16 QAM, as well as 64 QAM, and each modulation scheme will be consisting of different bits per symbol which it can be transmitted, right? Along with that, there is also called coding scheme. So coding scheme is nothing but the error correction scheme, right? And it affects the efficiency of the particular modulation scheme. This particular factor also affects the throughput in LT. The final factor which affects the throughput LT is also called as UE category. So if you are aware of the attach procedure, you know that in attach, this is the parameter which has been transmitted by UE, which basically gives us a detailed description about what are the various features or which a particular UE can support. Okay, so this UE category can also affect the throughput in LT. So, if we discuss in detail about the first factor, that is the available bandwidth in LT. So, as I told earlier, that in LT there is a flexible bandwidth concept, right? So, LT can support this amount of bandwidth and this particular bandwidths, right? First, the 1.4 megahertz, 3 megahertz, 5 megahertz, 10 megahertz, 15 megahertz, and also 20 megahertz, right? And with each bandwidth means actually what happens is that entire, if you let's say if you take an example of 20 megahertz bandwidth, okay, this entire 20 megahertz bandwidth will not be entirely used for the transmission, okay. A certain amount of this bandwidth will be used as a guard band as well, and the remaining bandwidth will be called as the effective bandwidth. Okay, so if you take the example of this 20 megahertz bandwidth and calculate the throughput of it, so the guard band of this 20 megahertz bandwidth will be the 10% of it. Okay, so the 10% of this 20 megahertz will be uh, 2 megahertz, right? And hence this 2 megahertz will be the guard band, and hence the effective bandwidth which remains is the 18 megahertz, right? So we can say that if you see this particular table, so this 18 megahertz is what actually it will be transmitted, and here all the resource block and all the information which will be transmitted will be consisting inside it, and the remaining 2 megahertz will be used as a guard band, right? And also we know that the carrier spacing in LT is 15 kilohertz. That is, in between any two sub carrier, the subspacing difference is actually 15 kilohertz. And also, in a resource block, as we know, there are 12 subcarriers, right? And hence, the bandwidth of one resource block will be calculated as following. So, if you want to calculate the bandwidth of one resource block, so it will be 15 kilohertz, which is actually the subcarrier spacing between two subcarriers, multiplied with 12. 12 is nothing but is the number of subcarriers in one resource block. And hence, this product actually gives us 180 kilohertz, right? So from this, we came to a conclusion that the bandwidth of one resource block of a 20 megahertz bandwidth is nothing but it's 180 kilohertz, right? And from this particular value, we'll be calculating the number of resource block that can be accommodated in the effective bandwidth of 18 megahertz. 2 megahertz we are not the remaining 2 megahertz we are not using because it has been considered for guard band. So the only bandwidth remaining bandwidth, that is 18 megahertz, which is also called as effective bandwidth. There only will be transporting the our resource block. So the number of resource block that can be accommodated in this effective bandwidth can be calculated as 18 megahertz divided by 18 kilohertz. Okay, so it basically gives us a number of 100. So it means that the 100 resource block can be accommodated in this particular bandwidth. Okay, so this is very important. You need to remember this number, which we'll be using in further in our further calculation, right? So 100 resource block can be accommodated in the 18 megahertz effective bandwidth. Okay. Um, in a similar fashion, we can also calculate the effective bandwidth, or we can say the number of resource block for other bandwidth as well. Okay, as I told that beside 20 megahertz bandwidth, there are also certain other bandwidths which NLT can support. So for that particular bandwidths, also we can have different resource block. Okay, so and the most important point here which we need to take a point of is that higher is the bandwidth, more will be the resource block. Okay, so for this is the maximum resource block which actually it can accommodate, because 20 megahertz is the maximum bandwidth which NLT can support. So beside that, we have the bandwidths like 1.4 megahertz, right, 3 megahertz, 5 megahertz. So all of them can have a certain value which it can support, a resource block it can support. For calculating it, but just what we need to do, we need to first calculate the guard band of that regular bandwidth by taking 10% of it, and then after we get that particular value, what we can do, we can calculate the bandwidth of one resource block using this same formula. 15 kilohertz will be same as it is a carrier spacing between the two subcarriers multiplied by 2 or 12. So this value will remain consistent for all the other bandwidths as well, but the difference will be here, the effective bandwidth. So this effective bandwidth for different bandwidth will be different, as we'll be taking the 10% of that particular bandwidth. And hence, after getting the effective bandwidth, what we can do, we can multiply it with the bandwidth of one resource block, that is 180 kilohertz, and that will give us the number of resource block. The other factor which affects the throughput in LT is the multiplexing technique. So as we know, in LT there are two types of multiplexing technique, right? One is the FDD, other is the TDD, right? FDD is also known as the paired spectrum. Okay, so why it is called as paired spectrum? Because as we know, if we consider the 20 megahertz bandwidth, okay, if we consider the 20 megahertz bandwidth, okay, so in FDD what it will happen, it will be if it will be allocated for uplink separately and downlink separately. Okay, it means that and hence it isn't paired, right? Pair, because for uplink we have allocated 20 megahertz bandwidth, and for downlink also we have allocated a separate 20 megahertz bandwidth. Okay, but unlike this, TDD is actually unpaired spectrum. So why it is unpaired spectrum? Because in TDD, as we know, this 20 megahertz bandwidth will be distributed across this uplink and downlink. It means that this uplink and downlink will be using the same 20 megahertz bandwidth. So it is an unpaired spectrum. Okay, so FDD is also symmetric in it has a symmetric nature. So why it has a symmetric nature? Because as I told that this 20 megahertz is separated equally for separately allocated for uplink as well as downlink, right? So it means that the amount of bandwidth which has been allocated to UL will be same as the bandwidth which has been assigned to the downlink as well. Okay, so but this TDD is actually asymmetric in nature. Okay, so why it is asymmetric? Because in TDD this 20 megahertz bandwidth is distributed across the entire UL and DL. Okay, so sometimes it can happen that UL can cover a large portion of this 20 megahertz bandwidth, and sometimes it can happen that a certain portion of large portion of bandwidth can be covered by the DL. So it is user specific. Okay, depending on the user case use case, it can do that. Okay, and also if you see this table, okay, you can see that this is the TDD frame configuration. Okay, so there are different TDD frame configuration, and each frame configuration has different configuration of UL downlink and uplink. Okay, and also it has a special subframe also. So if you have seen our LT frame video, LT frame structure video, so there we have discussed this in detail. Okay, so if you haven't watched it, you can watch and understand this concept. Okay, so you can see this different configuration out there, and in each configuration basically consists of different downlink, special subframe, and uplink configuration. Okay, for example, if you see the TDD frame configuration 2, you can see that the number of downlink DL which consists here is 6. Okay, and number of UL is 2, and number of special subframe is 2. Okay, so these particular factors in this way can affect the throughput in LTE as well. The third factor which affects the throughput in LTE is modulation and coding scheme. Okay, so as we know, there are certain modulation scheme which LTE can support. Okay, one is a QPSK, second one is 16 QAM, and the final is the 64 QAM. Okay, as we know that in QPSK, 2 bits per symbol can be transmitted. 2 bits per symbol. In 16 QAM, you can transmit 4 bits per symbol. And finally, in 64 QAM, we can transmit 6 bits per symbol. Okay, so in this way, you can see that different modulation scheme has a different amount of bits which it can transmit, right? And hence, this can and hence, if you are using different modulation scheme, that it can also affect the throughput in LTE as well, right? And if you come to the coding part, okay, coding, as I told, is nothing but is besides the error correction scheme. Okay, error correction. So if we see the example of 16 QAM, okay, so the coding rate of the 16 QAM is 0.5, which means that if the data bits per symbol, if you haven't done the coding, is 4 bits only. Okay, 4 bits per symbol we can transmit. But if coding is involved, the data bits per symbol will be transmitted as 2. Okay, and the other remaining 2 bits will be as redundant. Okay, so in the same way we can calculate for QPSK and 64 QAM as well. Okay, and then we come to UE category. Okay, as I told, that UE category basically is the information that means what are the different capabilities that particular UE can support. Okay, so this UE category can affect these 3 factors. One is the number of antenna that are supported in ULDL. Okay, and then number of transport block size that in ULDL, and finally modulation scheme that is supported in ULDL. Okay, so these are the 3 important factors which a UE category can affect. Okay, which we need to know. Okay, finally we'll do the most important part in our video is the throughput calculation. Okay, so we'll first start with the FDD calculation first. Okay, and then we will also be proceeding with the FDD calculation as well. Okay, so for our calculation, we have basically considered 20 megahertz bandwidth. Okay, so if in a previous slide, what we have done, we have calculated how many resource block can be accommodated in a 20 megahertz bandwidth, right? So basically it was 18 megahertz, that was an effective bandwidth. So in 20 megahertz bandwidth, resource block of 100 can be accommodated, right? And there are and as we know that in one resource block, how many subcarriers are there? There are 12 subcarriers, right? So 100 resource blocks are there, out of which in one resource block there is 12 subcarriers. and one subframe, as we know, is of duration 1 millisecond. Okay, and further, this one subframe can be divided into two time slots, right? And in one time slots there are how many OFDM symbols? There are 7 OFDM symbols if we are considering the normal cyclic prefix, right? If we take the extended cyclic prefix, then there will be 6 OFDM symbols, right? So here we have considered a modulation scheme of 64 count. It means that in one OFDM symbol there will be 6 bits. Okay, so one OFDM symbol will be considering of 6 bits. Okay, so if we calculate the number of bits in a subframe, so this will be 100 RB. Okay, 100 RB multiplied with 12 subcarrier resource block, and then we'll multiply it with 7 OFDM symbols, right? Uh, and then uh, um, and then we'll be multiplying it 6 data bits in one OFDM symbol. Okay, so this combined product will give us the number of bits in a subframe, right? So which is actually 100,800 bits, right? So this is the number of bits which can be transmitted in a single subframe, right? So if we want to calculate the data rate, what we'll do, we'll be dividing this particular bits with the duration of the subframe, which is 1 millisecond, and hence it will give us the data rate, which is 100.8 Mbps, right? So if we combine the factor of the MIMO configuration, so here we have considered the MIMO configuration of 4 cross 4, right? So if we multiply this MIMO configuration of 4, right, with 100.8 Mbps, so this will give us 403.2 Mbps, right? And then if we also include the factor of 3 by 4 coding rate, so the effective data rate will be 3 by 4 multiplied with 403.2 Mbps, which is 300 Mbps, right? It means so finally we can conclude that if we consider a 20 megahertz bandwidth which consists of 100 resource block, okay, and considering the 4 cross 4 MIMO configuration with a 3 by 4 coding rate, so this will give us the data rate, effective data rate of 300 Mbps. This is the throughput calculation for 20 megahertz FDD. uh, in this way we can calculate, right? There is one another way also for calculating this 20 megahertz FDD by actually referring to an MCS index and TVS table. So there is a table called, you can see here. So this is the table. Okay, so this is the MCS index table, which also consists of TVS index, and this TVS index has this table, right? So as we know that we are considering the 100 PRB, right? So for this 100 PRB, the TVS index is 26, and the number of bits which it can support is 753676, right? So it means that in this 100 PRB, the MCH index is 26 and the TVS value is 75376, right? It means that, okay, this, let me correct this. This is 75376. Okay, so 75376 bits can be transmitted in a subframe. Okay, so now if you want to calculate the bits per subframe, what we'll do, we'll be dividing this 75376 with the duration of the subframe, which will give us the bits per second. Okay, so the bits per second here will be 75376,000 bits per second, right? Now if you consider the factor of the MIMO configuration, or you can say the antenna configuration, so here we have considered the antenna configuration of 4 cross 4, right? So if we multiply this value 75376 with 4, it gives us around 301.504 Mbps, which is approximately 300 Mbps. uh, it means that this both these two methods, which we the method which we used earlier and now the method which we use, both of them has gave us the same throughput value, right? That is 300 Mbps, right? But here we have used the table of TVS table, or you can say the MCS table, for the calculation. And in the previous video, in the previous method, we haven't used any table, right? But both of us has led us to the same value of throughput for same antenna configuration, right? Now, finally, we'll be calculating the throughput calculation for 20 megahertz TDD. Okay, so for calculating the throughput for the TDD configuration, we need to consider some configuration out here, right? So the consideration what we have done, that we have considered TDD configuration of 2. So what does this TDD configuration 2 means? Okay, so if you can go to this table, if you can see, this is the TDD configuration 2. So we here, what we have done, we have actually we have considered TDD configuration 3, right? So we have, for our calculation, we have considered TDD configuration 3, where there are 6 downlink subframe, 2 uplink subframe, and also there are 2 special subframe also, right? So here we have mentioned here that for TDD, we have used a TDD configuration of 2, where 6 subframes are available for downlink, 2 for uplink, and 2 is used as a special subframe, right? And also for the special subframe, we have used the configuration of 7, right? So if we go in this table, so we have considered that the configuration number 7. Okay, so in the configuration number 7, you can see that the downlink DWPTS value is 10, right? There are 10 OFDM symbols per subframe for DWPTS. For guard there are 2 OFDM symbols, and finally for UPPTS there are 2 OFDM symbols, right? Same thing we have mentioned here also, that for special subframe configuration, 10 OFDM symbols are used for DWPTS, 2 for UPPTS, and the remaining OFDM symbol for card period, right? Also, for the modulation scheme, we have used the 64 QAM, where, as we know, that in one OFDM symbol there are 6 bits, right? Finally, this is the formula for the downlink throughput for TDD configuration, right? Which is nothing but throughput by DL frame multiplied with its efficiency plus throughput by DWPTS multiplied with efficiency, whole bracket, multiplied by number of antenna. Okay, so what is this throughput? Okay, for understanding this throughput, what is this efficiency? How we can find the efficiency of this particular downlink frame, right? So if you see this table, as we know that we have considered the TDD configuration 2, right? So the for TDD configuration 2, we can see that there are 6 subframe available for DL in DL side, right? So it means that out of 10 subframe numbers, there are only 6 instances where we have transmitting the DL, right? So it means that its efficiency will be 60%, right? And for the special subframe, if we see, it is 2. It means that only 2 times we are transmitting the special subframe, right? So hence its efficiency will be 20%. So this we have used, that in case of efficiency for the downlink frame, it's 60%, multiplied with 75376 bits per millisecond. So this we got from the table, right? Plus 75376 bits per millisecond multiplied with 20%. 20% is nothing but is the efficiency of the special subframe. Okay, this DWPTS come inside this special subframe. Okay, multiplied with 10 by 14. 10 by 14 is nothing but the code rate. Okay, and whole multiplied by 2, which actually give us approximately 112 Mbps. Okay, it means that the formula for DL, the output of DL throughput for this configuration for category 3 UV, it is actually nothing but 112 Mbps. Okay, same formula we can use for the uplink throughput also, but the only thing will be different is that instead of this, there will be UL frame, and here will be UPPTS. Okay, and everything remains the same, or it will give us a certain value for UL throughput as well. Okay, so this was our complete video on throughput calculation, uh, where we have discussed 2 different methods to calculate the throughput calculation for FDD. Okay, 2 different approaches we have taken. Okay, to calculate the FDD, and we found that both the method gave us same value for the throughput. Okay, and then we have also calculated the throughput for TDD as well. Okay, for both UL and DL we have calculated, right? So hope you all like this video. Please subscribe our channel for more videos, and we'll be coming with more technical videos here. So keep supporting us. Thank you.